Write 0.999 with the nines continuing forever. It feels obvious that this number must be smaller than 1. Infinitely close perhaps, but still missing one final sliver. Now try to point to that sliver. How wide is it? Where does it sit on the number line? And what digit could you add to reach one when there is no last 9 to add it after? The strange answer is that the gap is not tiny. The gap is exactly 0. 0.9 repeating and 1 are not neighboring numbers. They are two different names for the same point. That sounds like a trick, so let us build the result 4 different ways and see where infinity changes the rules. This is symmetry. Let's find out why. First, we need to separate a very long decimal from an infinite one. Start with 0.9. The distance from 0.9 to 1 is 1/10. Add another 9 and get 0.99. The distance is now 1/100th. Add a third 9 and the distance becomes 1,000th. Every extra 9 divides the remaining gap by 10. After 10 nines, there is still a gap, 1/10,000,000th wide. After a million nines, there is still a gap, absurdly small but positive. Any decimal with a last 9 is less than 1. That fact is completely true, and it is exactly why our intuition protests. We imagine repeating forever as merely an outrageously long finite list. But infinity is not a very large stopping point. It means the stopping point never exists. Here is the difference in one picture. On the left, write a decimal with 1 million nines and then stop. Somewhere, unimaginably far to the right, that decimal has a final digit. Its difference from 1 is a 1 shifted 1 million places after the decimal point. On the right, write 0.9 repeating. There is no final digit, so there is no position where that lonely one can be placed. The expression 1 minus 0.9 repeating does not become 0.000, followed eventually by a 1. Eventually never arrives. Every finite decimal place is already occupied by a 0 in the supposed difference. A real decimal made entirely of zeros is simply 0. We can describe the same process without trusting a picture. Let the first approximation be 0.9, the second 0.99, and so on. The nth approximation is 1 minus 10 to the negative n. Its gap from 1 is 10 to the negative n. As n grows, that gap can be made smaller than any positive distance you name. Smaller than 1,000th, 1 trillionth, or 1 divided by a number with a billion zeros. The infinite decimal means the limit of this sequence, and the only real number whose distance from 1 is smaller than every positive distance is 1 itself. The approximations are always below 1. Their limit does not have to be. Now let ordinary algebra force the two decimals together. Call 0.9 repeating x. This is not a guess about x, it is just a name. Now multiply both sides by 10. Multiplying a decimal by 10 shifts every digit one place left, so 10x equals 9.999 repeating. Notice what happened. The infinite tail after the decimal point is exactly the same tail we started with. That is the special power of a repeating decimal. Shifting it does not create a new pattern. It exposes one whole 9 in front, while leaving an identical copy of x behind. We have turned an infinite object into two expressions whose infinite parts line up perfectly. Subtract the first line from the second. On the left, 10x minus x is 9x. On the right, 9.9 repeating minus 0.9 repeating is exactly 9. Every digit in the endless tail cancels against the identical digit below it. So 9x equals 9. Divide both sides by 9 and x equals 1. But x was our name for 0.9 repeating. Therefore 0.9 repeating equals 1. Nothing was rounded. We did not chop the decimal after a convenient number of places. The cancellation works precisely because both tails continue forever and match digit for digit. A common objection says the algebra quietly ignored a final digit. But there is no final digit to mishandle. To see why alignment is legitimate, perform the same trick on a finite version. Let I be 0.999 with exactly 3 nines. 10y is 9.99. Subtracting y leaves 8.991, not 9, because the shifted rows stop at different places. A tiny remainder survives at the end. for 0.9 repeating, the rows never stop, so there is no exposed end where a remainder can survive. The algebra is not hiding the difference. It shows exactly which difference exists in the finite case and exactly why it disappears in the infinite case. A familiar fraction reaches the same answer by a completely different road. Divide 1 by 3 using long division. 3 does not fit into one whole, so write 0 and move to tenths. 3 fits into 10 3 times, leaving a remainder of 1. Bring down another 0. We are back at 10, so the next digit is 3, and the remainder is 1 again. The exact same state repeats forever. That is why 1/3 equals 0.333 repeating. The repeating decimal is not an approximation someone chose. It is the exact record of a division algorithm that never reaches remainder 0. Now multiply both descriptions of 1/3 by 3. The fraction side is immediate. 3 times 1/3 equals 1. The decimal side gives 3 times 0.3 repeating, which is 0.9 repeating. Equal quantities stay equal when multiplied by the same number, so 1 equals 0.9 repeating. If you reject that conclusion, you must also reject either that 1/3 has the decimal 0.3 repeating, or that 3/3 make 1. There is no spare sliver left over. 3 equal thirds tile the whole unit exactly, whether the thirds are written as fractions or decimals. This is not a weird accident unique to nines. Every terminating decimal has a second representation ending in repeating nines. 1/2 is 0.5, but it is also 0.4999 repeating. 1/4 is 0.25, but also 0.24999 repeating. Why? Replace the final unit in the last shown place by an endless tail that fills exactly that unit from below. In base 10, the tail is all nines. In base 2, the same phenomenon uses all ones. Positional notation is a naming system, and at these boundary points the system gives one number 2 valid names. Next, we will build the decimal as an infinite geometric machine. The first 9 in 0.9 repeating means 9/10ths. The second means 9/100ths. The third means 9/1000ths. So the decimal is a sum, 9/10ths plus 9/100ths plus 9/1000ths, continuing forever. Each term is 1/10 of the previous term. That makes a geometric series with first term 9/10ths and common ratio 1/10. The standard sum is the first term divided by 1 minus the ratio. 9/10ths divided by 9/10ths equals 1. But rather than merely quote the formula, let us watch that sum physically fill a hole. Draw a unit square, shade 9/10ths of it. The unshaded strip has area 1/10. Now shade 9/10ths of that remaining strip. You add 9/100ths of the original square, leaving 1/100th. Repeat, shade 9/10ths of what remains, leaving 1/1000th. After every finite step, a thin strip survives, but the surviving area is divided by 10 each time. In the infinite construction, its width becomes smaller than every positive width. No positive strip remains. The shaded pieces total the entire square, and their areas are exactly 9/10ths plus 9/100ths plus 9/1000ths forever. We can derive the geometric formula from the same cancellation as before. Call the infinite sum S, multiply S by 1/10. Every term shifts one place to the right, so 1/10 S begins with 9/100ths. Subtract 1/10 S from S. All terms except the first cancel, leaving 9/10ths. Therefore 9/10ths S equals 9/10ths, so S equals 1. The decimal proof, the algebra proof, and the area proof are not separate coincidences. They are the same self-similar structure viewed as digits, equations, and geometry. Infinity becomes manageable when removing the first piece leaves a scaled copy of the whole. If a gap still exists, the number line must give it somewhere to hide. Suppose 0.9 repeating is less than 1. Then their difference, call it D, must be a positive real number. Any positive decimal has a first non-zero digit somewhere. Maybe it begins at the 10th place, the millionth place, or much farther out. But there is a first place where 0 becomes something positive. Choose that position. Now look at 0.9 repeating. It has a 9 in that position, and in every position after it. The gap after that many 9s is already smaller than 1 unit in the chosen position. So D would have to be both at least that unit and smaller than it. the alleged first non-zero digit cannot exist. There is an even cleaner number line test. If two real numbers are different, there is another real number strictly between them. In fact, their average always works, so if 0.9 repeating were below 1, their midpoint would sit in the gap. But what could its decimal expansion be? It must agree with 0.9 repeating through every finite place, because changing any digit would put it below one of the nines, or at least at 1. A number that agrees with 0.9 repeating in every decimal place is 0.9 repeating itself. The supposed midpoint collapses onto an endpoint. There is no room between the two labels because they mark one location. Another objection imagines an infinitesimal gap, positive but smaller than every ordinary positive number. Such objects can be defined in extended number systems, and they are useful in advanced mathematics. But the standard real numbers used for measurement, algebra, and calculus contain no positive infinitesimal. Their completeness says that a bounded increasing sequence reaches a real limit, and the sequence 0.9, 0.99, 0.999 is bounded above by 1. Its least upper bound is 1. Inside the real number line, there is no extra point immediately before 1. Any proposed point leaves room for another decimal closer still. The puzzle ends when we separate numbers from the names we give them. A decimal expansion is an address for a point on the number line. Usually each point has one address, but terminating decimals sit on a boundary between two naming patterns. 0.5000 forever approaches the point from the exact terminating side. 0.4999 forever approaches the same point from below. This resembles the way the angles 0 degrees and 360 degrees name the same direction, or how midnight can be written as the end of one day and the start of the next. The symbols differ because our notation wraps at a boundary. The mathematical object underneath does not split in two. This also explains why calculators sometimes display 0.9999 after a calculation that should equal 1. A computer usually stores only finitely many binary digits. Rounding errors can leave a nearby approximation, such as 0.999999, with a genuine last digit and therefore a genuine gap. That finite machine value is not the mathematical object 0.9 repeating. One has a final stored digit, the other is defined by an infinite limit. The screen can look similar while the meanings are different. Never use a finite calculator display as evidence against an infinite decimal statement. Now return to the opening question. How large is 1 minus 0.9 repeating? Algebra says 0. 3 exact thirds say 0. The geometric series fills the unit square with no area left. The number line offers no midpoint and no first non-zero digit for a gap. 4 constructions. 1 answer. The unsettling part was never the arithmetic. It was the assumption that an infinite process must stop at some hidden final stage. It does not. Every finite approximation is less than 1, while the value defined by the entire endless sequence is 1. Infinity did not make two neighboring numbers impossibly close. It gave one number two perfectly valid names. 0.9 repeating is not almost 1. It is 1 written from the other side. Thank you for watching Symmetry, where math, physics, and chemistry are explained deeply, not dumbed down. If this proof changed the way infinity feels, subscribe for the next construction.